Greetings, my statistics friends. In this problem from Chapter 9, homework, we are going to look at number 7. And number 7 corresponds to section 9.4 and question 1. So this is a multiple regression model. So that means there are multiple variables. And we use this notation x1, x2, x3, x4 because frankly, if you have too many letters, you would run out of letters, right, in the alphabet. So instead of saying Y and X and Z, we do X1, which is the output, and then X2, X3, X4 are inputs into the function. So this function named X1 has multiple inputs, 1, 2, 3 inputs. So part A, which variable is the response variable? So the response is the output of the function. So x1 is the response variable. Which variables are the explanatory variables? So explanatory variables are the inputs of a function. So x2, x3, and x4 are the inputs. So output is response, input is explanatory. Which number is the constant term? Well, this term 1.9 in my example doesn't have a variable, right? So that's not going to vary. So the constant is 1.9. Then it says list the coefficients with the corresponding explanatory values. So the constant is 1.9. The coefficient of x2 is 3.4. 3.4. The coefficient of x3 is negative 8. So minus 8. And the coefficient of x4 is positive 1.7. So that's just reading off the actual model itself. Part C. If x2 equals 3, x3 equals 4, and x4 equals 9, what is the predicted value for x1? So all we're doing here is plugging in those values that were given into the function itself. So let's take a look at that. So we have x1 equals 1.9 plus 3.4 times x2 minus 8 times x3 plus 1.7 times x4. And we're asked to evaluate when we have the situation of x2 equaling 3, x3 equaling 4, and x4 equaling 9. So all that means I have to do is plug in x2 in for x2, x3 in for x3, and x4 in for x4. So let me do that. And once again, all I did was take x2 and plug it in to the spot that it belonged. And I took x3 and plugged it into the spot that it belonged. And I took x4 and plugged it into the spot that it belonged. So then I just typed that out in my calculator, equal to negative 4.6. So I type in negative 4.6. And then part D says, explain how each coefficient can be thought of as a slope under certain conditions. So I'll let you think about that answer yourself, but remember that a slope of a line is the rate of change. So if we hold certain things fixed, then basically what I say is just take them out of the equation. So those things are not changing anything because you're holding them fixed. So the slope is fixed, it's not doing anything. So suppose x3 and x4 were held at a fixed but arbitrary values of x2 and increased by 1 unit. And what we're saying that we want to do is fix x3 and x4 are fixed. So this is not exactly mathematically sound. I can kind of think of it as just crossing out the terms that have those variables. And that's the idea. So x3 and x4 are held at a fixed but arbitrary value, and x2 increased by 1 unit. So what would the change be in x1? Think about then what's happening to this term if I'm plugging in x2 equals plus 1 unit. So I'm putting that into that term. Well, then x1 will change by 3.4 times plus 1. And so the change will be positive 3.4. What if it's changed by 2 units? So x2 equals plus 2 units. So x1 will change 3.4 times positive 2 units. Okay, and so I multiply 3.4 times 2 and I get 6.8. Right, that's the idea. And then if it decreased, I'd put in a negative. So let's say x1 will change by negative 2 units. So then I put in 3.4 times negative 2, and I'd get negative 6.8. That would be what the change is. So that's how you answer those particular questions about holding things constant. So this first one would be 3.4, and the second one would be 6.8. And then if I decrease by 4 units, well, then I take 3.4 and multiply it by negative 4 because it's decreasing, and I get negative 13.6. Okay, so that covers all of the parts through part E. So then it says, suppose that n equals 11 data values are used to construct the given regression equation, and that the standard error for x2 is 0.356. Construct a 99% confidence interval for the coefficient of x2. So how do we do that? This is something that there's a formula in our book for. So let's take a look at how to do this problem. So we have n equals 11 data points. And we're told that the standard error for our x2 coefficient is equal to 0.356. And then we're to find a 99% confidence interval. And so we'll need a lower and an upper interval. Okay? So the first thing is we have to find the degrees of freedom for our 99% confidence interval. And our book tells us that we use the formula n minus k minus 1, where k equals the number of explanatory values. So in this case, k equals 3 because we had an x2, an x3, and an x4. So then what we have to do is we have n equals 11, so we have 11 minus 3 minus 1 degrees of freedom. So 11 minus 3 minus 1 is 7. So that is 7 degrees of freedom. So then I look on my student's t table. My t sub c in this case is 3.499. That's the first thing I have to do, is find that t sub c for 7 degrees of freedom and the 99% confidence interval. So this is B2 for short. So this is the coefficient. And my coefficient in this case for x2 is 3.4. So b2 equals 3.4. And to find the upper, I do b2 plus my t sub c times my standard error for 2. So that would equal 3.4 plus 3.499 times the standard error that we were given, 0.356. 0.356. So where again did all these numbers come from? Well, this 3.4 comes from the coefficient of x2. And the coefficient of x2 is 3.4. And that's because we're talking about x2. That's where that number came from. Where did this 3.499 come from? Well, I looked up 11 minus 3 minus 1 degrees of freedom on my chart for 0.99 critical value, and I found that 3.499. That's where that number came from. And where did this 0.356 come from? Well, the problem told us that the standard error for that coefficient was 0.0356. So that's my upper value. And so when I type that in my calculator, and I got 4.65 to 2 decimal places. And the lower is the same, but I replace the positive sign with a negative sign instead of plus or minus. So t sub c times the standard error of 2. So this would be 3.4 minus 3.499 times 0.356. And I get 2.15 rounded to 2 decimal places. 0.15. And my upper limit is 4.65. All right, let's look at F. So using the information of part E and a level of significance of 10%, test the claim that the coefficient x2 is different from 0. So, once again, I have to find this t critical value. How do I find this t critical value? Well, I use my student's t distribution with n minus k minus 1 degrees of freedom. And when I do that, I get 7 degrees of freedom. And from my chart, and a 10%, so I'm looking for 0.90, and I go down to 7, and I get 1.895. 1.895. They want us to round that to 2 decimal places, so I have to do 1.90 for 2 decimal places. So that's the critical t, plus or minus. And then there's this t statistic. Well, how do we find that? So we need to find that t, so that's t is equal to, and the formula in our book says we use the coefficient, and they call that bi, and divide that by the standard error of the number si. So in this particular example, we're talking about b3 divided by se3, the standard error 3. So the coefficient for x2, or b3 as it's called, is 3.4, and the standard error was 0.356. And so then that's equal to 9.55. So this number would be 9.55. Okay, so then what's the conclusion? Well, remember when we are testing our beta, we're thinking about the slope of the line. So our test is, our null hypothesis is that our proposed slope is equal to 0, and an alternative hypothesis is that our proposed slope is not equal to 0. So that's also true in this case for multiple regression, except for we are testing each individual slope separately. So beta 2 for this question is equal to 0, as opposed to the alternative hypothesis is that beta 2 is not equal to 0. And so for regression, we just do a similar test to each of the slope coefficients. And remember, if we show that the slope is not equal to 0, we would reject the null hypothesis in favor of the fact that we are convinced that the slope is not equal to 0 and therefore is relevant to the model. In this particular case, we are going to reject the null hypothesis and say that there is sufficient evidence that beta 2 is different from 0. And remember, if in a regression line, if your slope is equal to 0 or could possibly be equal to 0, then that's no good, right? That's not something we want. So this last question explained how the conclusion of this test would affect the regression equation. Well, there's lots of stuff going on here, but if beta 2, if we conclude that beta 2 is not different from 0, we would remove x2 from the model, and that's the one we want. Okay, so let's check our answers. Hopefully we typed everything in correctly. And it looks like everything we did is perfectly good. If you have any questions, please let me know.